Right now, in the deepest, most inaccessible canyon on Earth, China is breaking ground on a $167 billion engineering project. To understand the scale of what's happening, look at this. This is the Three Gorges Dam. At 22.5 gigawatts, it holds the current human record for hydroelectric generation. The new Medog Dam is designed to produce 60 gigawatts, nearly tripling that output. This map shows how that much power is physically possible. The Yarlung Tsangpo River travels across the Tibetan Plateau and then hits a severe geographic anomaly. In a span of just 50 kilometers, the riverbed drops 2,000 meters in elevation. But that same water doesn't stay in China. It flows immediately south, becoming the Brahmaputra River in India and then the Jamuna in Bangladesh. This single river provides the drinking water for 300 million people, including the 30 million residents of Assam who rely on its flow for their crops. Construction began in July 2025, moving ahead in a region where no formal international treaties exist to govern the river's shared flow. Once complete, the project will establish a physical infrastructure that precedes any potential diplomatic framework. To build anything in a completely roadless environment, you have to build the environment first. Before a single wall rises, billions of dollars are spent laying access networks, cutting a main highway through the mountains, and wiring in the high-voltage power lines needed to run the construction equipment. Even with a primary road, the canyon's vertical terrain forces the site to run on heavy-lift helicopters and aerial cable cars. Workers cross the gorge in 8 minutes instead of a 3-hour drive, while precision parts that can't wait for a road extension drop in from above. The next step is moving the Yarlung Tsangpo itself. During monsoon season, this river runs at 14,000 cubic meters per second. Crews blast through 200-million-year-old Cambrian granite, clearing 30 meters of solid rock in 6 weeks to create a temporary diversion channel. With the temporary channel open, the original riverbed slows and drains. For the first time in geological history, the exact ground where the dam will stand is exposed to the air, providing the bare, clean foundation rock required to support the structure. The permanent path for all this water will actually go through the surrounding mountains. Crews are boring 4 separate 20-kilometer tunnels straight through the Himalayan granite to route the flow past the central dam sites. Doing that requires a 14-meter diameter tunnel boring machine. Weighing 4,000 tons, it is the largest ever deployed in Asia, shipped in 300 pieces and taking 4 full months just to assemble on site. The machine's head, armed with 240 tungsten carbide disc cutters, grinds into the dark rock face. It runs continuously on 24-hour schedules for 51 uninterrupted months, battling extreme heat and frequent geological fracturing. As the machine advances, workers immediately line the fresh excavation with precast concrete segments. Placing 1 ring every 40 minutes, they ensure the tunnel supports its own weight and stops the mountain from collapsing inward. These massive voids are then lined with steel piping, known as penstocks. The result is a series of calibrated, high-pressure tubes designed to efficiently capture the kinetic energy of water traveling at 60 meters per second. To safely capture a 2,000-meter drop, the river routes through 5 distinct cascade dams, stepping down the steep canyon. These dams are built using roller-compacted concrete. Dump trucks deposit the mix in continuous 300-millimeter layers, which are immediately flattened by vibratory rollers before setting. At the base of these cascades lie the powerhouses, home to the energy extractors. Crews install 60 individual Francis turbines into deep excavated pits, with each unit rated to generate 1,000 megawatts of electricity. Getting those parts here requires a long logistical chain. A 280-ton turbine runner must be shipped by heavy rail to Lhasa before finishing the final 500 kilometers on freight trucks navigating steep mountain passes. Once all 5 cascades top out, the final turbine runners are aligned to a fraction of a millimeter. The kinetic energy of the river is locked into a synchronized 60-machine power grid. By the target completion date of 2033, 60 gigawatts of electricity will leave Tibet. It travels over 4,000 kilometers via ultra-high voltage transmission lines to its final destination, fueling the morning commute and industrial hubs of eastern China. Back at the canyon, the spent water exits the powerhouse tailrace tunnels, returning to the riverbed. Just 25 kilometers downstream from the last concrete wall, it crosses an invisible border into India. Downstream governments are acutely aware of this shift. Diplomats and monitors watch the water levels constantly from their side of the border, forced into a passive role with no legal standing to inspect what sits upstream. Physically, China is not consuming the water. As this schematic shows, the exact same volume of water that enters the intake flows out the exit. The dams simply use the vertical drop to spin the turbines before releasing it. But that physical pause gives the dam operators control over the river's schedule. The timing and volume of downstream surges will no longer be determined by natural Himalayan monsoons. It will be dictated by the daily electricity demands of the Chinese grid. By 2033, this complex will generate more electricity from a single river than any other project in history. But it also places the volume and timing of a shared water source under a single, unregulated control point, decisions that will directly affect the 300 million people living downstream.